We can begin now. Welcome back, everyone. We'll have now the second of the two lectures by David on many-body localization. David, start.
Okay. So where I stopped yesterday, I was just getting started on discussing many-body localization in one dimension with short-range interactions. So just to keep things concrete and familiar, I'm going to work with the much-studied random field Heisenberg chain. That's the standard model of MBL. So that's written here, although in a slightly different notation than normal. My random fields are uniformly distributed between -1 and 1, and then my coupling is J, which couples produces the Heisenberg coupling along the chain. And the interesting regime where we have MBL is when J is small. And we're looking not at low energy states of this, we're looking at typical states which are near zero energy. So if they were thermal, or when they are thermal in the thermal phase, they're at temperature infinity. Okay, so the model really just has one, well, the model only has, well, it's got two parameters. It's got the length, so I have an open chain with ends. So it's got the length and the coupling J. And so I'll draw a phase diagram here, phase diagram in quotes, right? Of course, these are not thermodynamic phases. This is only about dynamics at infinite temperature. The thermodynamics along here is completely trivial. And then this phase diagram is kind of mixed in its meaning. Over here at this end, I'm talking about the infinite system, whereas over here, I'm talking about the behavior of finite systems. So in that sense, it's a composite. Yeah, so let's start in the thermal regime. So the part of this that's, well, best established, shall we say. So here, this is now strong enough couplings between the spins along the chain such that the system thermalizes well, even for this size systems that can be exactly diagonalized. So here in the thermal regime, systems with length less than or of order around 20 thermalize well. The eigenstates obey ETH rather well. The energy level statistics are very close to random matrix. And the precision of this thermalization increases strongly. So as you go to larger L, these statements, ETH, eigenstates obeying ETH, and random matrix level statistics get strongly better rapidly as you increase L. So the evidence for thermalization over here is very good. Now, if you go to extremely large J, where the Heisenberg model is the dominant term and the random field is a small perturbation, it again becomes a non-trivial question because this problem is integrable. But I'm nowhere near that regime, right? So there's a, if I went way off far over that way, there's interesting open questions. But there's an intermediate regime here with J of order 1, or even down to a half or so, where this is very clear. Okay, so that's sort of the one part of this where there's, I think, nobody is questioning. Now, when you do the finite size systems, you find that at some point here, which happens to be around 0.15 in this notation, the eigenstates change to being well localized. Of course, there's we're talking about quite small systems, there's a broad crossover. So here, and we've named this regime here, the pre-thermal MBL regime. The idea is that it thermalizes, but on the scale we're studying, it looks like it's MBL. So MBL is its behavior before it thermalizes at much larger system sizes and much longer times than you can get to. Okay, so here the eigenstates are well localized for the size systems you can study. But we have good theoretical arguments that the system does thermalize. Okay, and then quite recently, and I'll probably get to this later, although time might run out, we've been able to put a bound on where the phase transition is, assuming the phase transition is the avalanche transition, and the surprising thing was that bound was at this number, 0.03, much smaller than this number. And that opened up this great big intermediate regime, which is not really the MBL phase, but it's acting MBL at the system sizes we can study. And that this regime was so big hadn't been appreciated before. And then in the history of this subject for many years until quite recently, people were looking for the phase transition here. Because of course you do the numerics, you see thermal behavior, MBL behavior, and you'd think the phase transition is here. But it never quite made sense as a phase transition. And I think now we realize, now the conclusion is it's just a crossover. It's more like a glass transition, which is in the dynamics, but it's not anything sharp. It's just a very strong change in the dynamics. So the current picture of this is this here, this crossover from thermal to pre-thermal MBL. It's not a phase transition. And we now know it's actually quite far from the actual phase transition. And my feeling is it's this and the regime nearby in this end of the pre-thermal regime. That's the regime of physical interest and accessibility. But this is accessible. We can see this crossover. And so what happens just beyond it here in the pre-thermal regime is sort of the next thing that we should figure out. And this phase transition is so deep in here that it's something that we're not going to figure out from experiment or numerics. This really needs very strong theoretical work to settle that question to everyone's satisfaction. So the phase transition, I would say it's of theoretical interest, but it's really not directly accessible. And because of that, I will start focusing here for the next bit of my talk, because I think that's where the priority should be. Okay, so before I erase any questions, this is sort of the big picture, and what I'm going to do now is focus right around here, because I think that's the regime we should focus on.
There are a couple of questions, David. Yeah.
Yeah.
So David, you're going to explain like how you characterize the pre-thermal phase, right?
Yeah. Yeah, but basically, I think I sort of said the eigenstates are well localized, far from ETH, and we have a bound on the phase transition. So the system at the sizes we can access looks very much like MBL, but we have good arguments that in the limit of large L it will thermalize, or not that it will thermalize, but good arguments that it's not in the MBL phase. So that's what I mean by this regime. It's not in the MBL phase, but it looks MBL at the sizes we can access.
Okay, so like in glasses, like if you look at temporal correlations, they show some transition, right? In the
well, they show a very strong crossover. I think it's the same situation with structural glasses, that there may not be a real sharp transition there. It's just a rapid increase in the relaxation times.
Okay. Okay.
But that's controversial in glasses also, right?
So there is
Some
a
people want it to actually be a transition, right? And you can make limiting models where it is a transition, but in real structural glasses, I think there's no real strong evidence.
Sorry, another question. So I was just wondering how you got this 0.03 number. Is this from some bound or theoretical bound or something?
Well, theoretical and numerical. If I have time, I'll get to that at the end.
Okay.
It's a combination of theory and numerics. That's in the paper I'll mention just next.
In the chat, there's a question in the chat which says, I can read it out. There's a question by Nilotpal. Is the bound on the phase transition based on the assumption of existence of L bits?
Well, if there are no L bits, the bound is still true, because if there are no L bits, JC is 0. So if you remove that assumption, this bound is still true. But yeah, the arguments are based on that, but if you remove that assumption, the bound is still true. So actually, I wanted to mention, so this crossover, at least has been studied quite a bit, and I just started erasing, but I wanted to mention these 2 papers from so Crowley and Chandran, and then Long, Crowley, Kumani, Chandran, and I believe at least David Long's on the list of participants, so you can talk to him. He may have a poster about this, I'm not sure. So they have a description of many aspects of this crossover that I think is quite nice. I'll say a little bit about that as I go along, but there's a lot more known than what I'm going to say. Okay, so right, so we're gonna focus. Let me just put the phase diagram back up here. So here's J. This crossover. Thermal regime. Of course, since this is the crossover, exactly where everything isn't sharply defined. I'm talking about the behavior of finite systems before we've taken a limit. Thermal regime. And so we're going to focus here. I think we have a reasonably good picture of what's happening in the crossover and in the thermal regime, at least many aspects of it. But what happens just a little bit into the pre-thermal regime, I think, is an open question. And the way I would say it is, if we go, let's say here, just a little bit beyond the regime that we've been able to make sense of so far, you can ask the question, how does a bath emerge here and normalize the system as L and T increase? And now we're talking about L and T just not so far beyond what we've been able to access so far, right? So I'm not. Yeah. Right, and as I'll say, there's a question here which isn't addressed by what's understood as far in this crossover. So we need more than what's been learned about this crossover to answer the question a bit past the crossover here. And then the JC, which is way over here, what's happening there probably isn't the right physics in this vicinity either. So the theory of the phase transition we have is about the avalanche instability, but there's no sign numerically of the avalanche happening and being an important factor up in this regime. So what's the okay. Now, one thing that is happening in this regime that we've learned about and we've learned how to study is many body resonances and near resonances. So that's what I want to talk about now. So body resonances, near resonances. And so, you know, in some sense, the study of the MBL regime and the MBL phase, looking for what's actually happening in there, you know, was neglected for a long time because the focus was on this crossover. And a lot of things, you look at them in the MBL phase and nothing's happening, right? And so it was sort of boring looking at the MBL phase because people hadn't found what to look for that's interesting. Okay, and so this is what I want to tell you about many body resonances and near resonances. And the papers I mentioned before from Crowley and Chandran and Long, Crowley, Kamani Chandran are about resonances. But let me mention a couple of the other recent papers about resonances. So there's Garrett, Chalker, our paper. Luis, Medica, Kamani. And then there was actually just very recently a posting, which I haven't really digested, but it's definitely about this topic. Biroli, Hartman, Garcia. So these are recent papers about resonances and near resonances. And what I'll be telling you about, a lot of it is from this paper here, our recent paper about this. Okay, so we're in a one-dimensional MBL model. We're in the pre-thermal regime, just a bit past the crossover. And we're asking what's going on here that's interesting that we can study. And that's what these are. Now, of course, you can study them all the way deep into the MBL phase, but I'm more interested in around here, sort of near the crossover. Okay, so as I said, we're in an MBL regime or phase where in a finite size system where the eigenstates are localized. And by that, I mean each spin from zero. Well, if the system thermalizes, we're at infinite temperature, the expectation values of the spins should be zero. And so if the eigenstates have substantially non-zero expectation values of the spin, typically bigger than a half, close to 1, That's what I mean by well-localized eigenstates. Almost all eigenstates and almost all sites will have this true. Of course, just by chance, there will occasionally be particular sites and particular eigenstates that have expectation values very close to zero, but that's that would be in an eigenstate where other spins had large expectation values. Okay, so we're in that regime. So most spins in most eigenstates, we can say, is it up or is it down? Just by looking at the sign of this expectation value, and it's well away from zero, so the sign is a significant thing. Okay. Now, right. The level spacing, as I've emphasized, is exponentially small in L. So eigenstates alpha, beta that are adjacent in energy are, if not resonant, they're near resonant. And so when I say a near resonance, what I mean is two states that are almost degenerate. They could be resonant if they were strongly coupled. And then they are resonant if they are strongly coupled, and I'll tell you what I mean by that. Okay. Okay. So these are adjacent in energy. We're in the localized phase, or not phase, we're in the localized regime. They're adjacent in energy, but if you look at the spin patterns, they're just unrelated random spin patterns. So Zi is of opposite sign on about a half of the sites. So these two eigenstates, they're very close in energy, and they differ across the whole system. They differ substantially across the whole system. Okay. So in order to couple these two eigenstates, we need a process that flips of order half the spin, so it's a high order process. Okay. Okay, so now I'm gonna focus on, well, this is what we did in this paper. Focus on end to end near resonances. And what that means is the first site in the chain and the last site of the chain are among the sites where one eigenstate has the spin up and the other eigenstate has the spin down. So of all the pairs of eigenstates that are adjacent in energy, I'm now restricting it to the ones where between alpha and beta, the first spin flips and the last spin flips. So that's a quarter of all these pairs of adjacent eigenstates. So I still have exponentially many such pairs of eigenstates, which are end-to-end near resonances. So there are two eigenstates, alpha and beta. They're adjacent in energy, and the end spins are of opposite sign in their expectation values between alpha and beta. Okay, and so what that looks like, for example, is you would have up, down, down. So this would be site 1, 2, 3, whoops. To site L, and then plus durations. Eigenstate. And then beta would have this spin down, spin up, and whatever in between. And again, plus plus fluctuations. But fluctuations are small enough that the expectation values of the spins are as indicated, the signs of the expectation values of the spins are as indicated. And then we would have eigenenergy here, and then E alpha minus E beta. Okay. So what I want to do now is to
Question.
quantify the level repulsion and the hybridization between alpha and beta to determine whether, to what extent is there a resonance between alpha and beta. That's what I'm going to define what I mean by that and show you how we do that. Questions?
Yeah. So for the two states, only the end states are end spins are flipped, and all the others.
No, half of the other ones are also going to be flipped because they're just
The others, okay, the others can be anything.
yeah, and typically half of them will be flipped.
Right, okay.
Although it turns out the cases where a lot fewer are flipped, it's not really any different. Because in order to have a resonance between alpha and beta, you need a process that's end-to-end, and it has to go the whole length of the chain. Whether it flips spins while it's doing that or not, that seems to not be that important, which is...
Okay, and what's fluctuations? I didn't understand. What do you mean by fluctuation?
Well, the eigenstate, this is, the eigenstate has a lot of weight on this configuration, but then it's got spin flips, right? Because we have a Hamiltonian, right? Remember the Hamiltonian has a spin flip term, right? It's got sigma I dot sigma I plus 1, which is going to flip spins. So the expectation values of the spins have the signs as I've drawn, but the actual wave function is a linear combination of all sorts of computational basis states with flip spins, right? And I'm just saying, this particular configuration will have a high amplitude, and then there'll be a whole bunch of other terms with flip spins due to this term in the Hamiltonian, but they will have lower amplitudes, and the expectation values will have the same signs as this term. Quantum fluctuations, typical, of course, they're not 0-point fluctuations because we're not in the ground state, right? But in an eigenstate of a Hamiltonian with non-commuting terms, you have, but yeah, it's analogous to 0-point fluctuations in a ground state. Other questions? Okay. Okay, so we've got these two states, alpha. Remember, they're eigenstates of the Hamiltonian, alpha and beta. They're adjacent in energy. And now we're gonna consider the block sphere spanned by them. So just a little two-state Hilbert space spanned by linear combinations of these two eigenstates. Okay, so here's that block sphere. Put alpha here, beta here. And then find...
David, a question.
Most localized basis A, B, with, since it's a basis, and we want A and B to be orthonormal on the block sphere. And that'll look like this. So A might be over here, B might be over here. And most localized means maximize how do we know it's localized? We know it's localized because the spins have expectation values which are well away from zero. So we want to maximize the expectation values of the spins. So we maximize sum over I A squared plus B to under B squared. So we're maximizing the squares of the expectation values of the spins. And by doing this, so over all possible pairs of opposite basis states on this block sphere, so it's only a two-dimensional manifold we're searching on, so finding the maximum is not hard. And when we maximize this, we found the most localized, by my definition, most localized pair of basis states. Okay.
Question.
Yeah.
If one makes a mistake in picking this, like, is there not mistake, but if one makes a choice which within this from within this manifold, choice of two states, or are we optimizing in finding what these two states are as well?
Well, it's just a surface of a sphere. So it's a very simple space to search. This function is
alpha and beta. Alpha and beta.
Function is nice and smooth on this surface, and so it's easy to find the maximum. Right? Of course, it doesn't define. We could swap A and B, and that'll be a second maximum. But it's easy to find it. And it's not like a spin glass where there's all sorts of maxima. It's not a complicated landscape. Because it's a low dimensional problem now. We're just looking at two eigenstates, one block sphere. Very simple. Okay, now the case of so what happens if we're in the NBL regime, most of the time you don't find a resonance, you just find a near resonance, and the near resonance is so near resonance means A is approximately alpha and B is approximately beta, meaning the eigenstates were about as localized as you can get. You can't get a more localized basis state by mixing together these two eigenstates. So basically it means alpha and beta are not linear combinations of more localized eigenstates. They happen to be very close in energy, and that's what I mean by near resonance, but they're not really resonant. Okay, so that's the near resonance, and then the resonance is the more interesting case. So resonance is alpha and beta are Schrodinger cat like linear combinations of A and B. A and B are much more localized than alpha and beta. A and B differ over the whole system, and so that's why, and then alpha and beta are linear combinations, so that would be the case when A and B are down kind of near the equator. Right, this is the case when A and B are right near alpha and beta. This is the case when they're down near the equator. And then the system really has a resonance. It's taken two localized basis states, and the Hamiltonian has mixed them into eigenstates that are Schrodinger cat. Okay. And these two basis states differ end to end. Okay, and now what we do is we use this basis AB to look at the Hamiltonian, and the Hamiltonian in this basis is HAA, HAB, star, BB. all the rest of the Hilbert space, we've just left it alone. So the Hamiltonian is diagonal, and it just has this little 2x2 block, because just in this little 2x2 Hilbert space, we've gone to the more localized basis. Okay. And then the near resonance is the case when HAB is much less than HAA minus HBB. Right, and if that's true, then this Hamiltonian, the eigenstates are basically just set by the diagonal elements, and this is EA, very close to EA, this is very close to EB, and this is a small perturbation. So that's the case of a near resonance, and the resonance is the case when HAB is greater than or of order HAA minus HBB. And here we're really going to have a resonance, and we're going to see the level repulsion. So there always is level repulsion in the MBL phase. It's just rare. You know, if you look around, you can find it, and this is a way to find it. The level statistics are close to Poisson level statistics without level repulsion, because most pairs of nearby eigenstates are not resonant. And so this doesn't make much level repulsion at all. But there are pairs, rare pairs of eigenstates that do have resonances and do have level repulsion. So this gives a systematic way of going in and finding that in your numerical data. Okay. Questions about that?
Question in the chat. David, yeah, I'll read it out. How is this resonance counting different from resonance counting for Anderson localization with many particles in the system? Or what difference does interaction make in this resonance, in these resonances?
Well, this is of the interacting system. So it's not, you know, this is something which is not at all related to any single particle model. So, yeah, I would say here the interactions are strong, for this consideration here, it's nothing like single particle problem. It's a regime where I guess I'm not haven't really thought about that, but I see no reason to think that a single particle problem would do anything approximately like this.
David, I
Yeah.
have a question about this maximization procedure. The value of the maximum also is important, right? Like you might, if you find a maximum, I mean, if you maximize it, but the value itself is near zero. So is it always guaranteed that you are significantly away from zero?
Yeah, well, we're in the NBL regime, so even alpha and beta, it's already way away from zero.
Okay.
So it's already reasonably large, and now when it's a near resonance, you only increase it a tiny bit by going from alpha to A, because A is very close to alpha. But it's already, you know, this is already quite large, because all of these things are of order 1. Right?
Okay.
Like 60% or 80% or something like this, or you know, even closer to 1. Now, when it's a resonance, you increase it, you know, going from alpha to A, you actually increase it quite a bit because you make it significantly more localized. By removing the Schrodinger, you know, having the Schrodinger cat state means, you know, some of the spins in A are up and in B they're down, and in alpha, they're both up and down, so the expectation value is small. So the resonant states typically have small expectation values of Z on the sites that are of opposite in A and B, because But yeah, there's no issue of it being near zero. Right. Of course, there's somewhere on the block sphere where it's near zero, but that's the minimum. You know, we're way away from there.
There's another question, David. Yeah. There's another question.
There is. Yeah, go ahead.
So when you were talking about this near resonances for this model that you were considering this, you also have to take care of the symmetry for the resonances, right?
Well, there's not much symmetry here. What do you mean?
So like, I mean, for your x-axis chain, I mean, the resonances can only
I have a random field, so there's not much symmetry left.
be for your Hamiltonian.
Oh, the resonances will be, yeah, right. Alpha and beta are in the same sector.
But
So
if you look at
alpha
this,
and beta, I should have said that, right? In this model in particular, where we have total SZ, I look within typically total SZ equals 0, or total SZ equals a half. And so alpha and beta are in the same total SZ sector so that they can possibly be resonant.
yeah, that is correct. But
I should have said that.
But when you look at the spectrum of the entire Hamiltonian, and if you really want to identify the SZ equals to 0 states, let's say, those states are not always nearby, right?
Well, let's just say, I should have said, yeah, let's just say L is even, and we're only looking in the total Z equals 0 sector.
Yeah, but if you keep
So now everything is total Z equals 0. Yeah, I should have said that. Thank you.
all right, but I have a confusion in the sense that, I mean, if you really like look at the spectrum of the entire Hamiltonian and you just identify the SZ equals to 0 sectors, it's not always true that.
Well, it's not goes to 0, it's equal to 0.
Yeah, okay, equal to 0.
And let's just restrict to that part of the Hilbert space only. So when we say the entire spectrum of the Hamiltonian, we mean the entire spectrum of the Hamiltonian with total Z equals 0.
Yes, and you were saying that if
and when I say adjacent in energy, I mean within that sector. Yes, I'm sorry, I was sloppy about that.
Okay, but if you go to thermodynamic limit, you expect that the difference will go to 0 because of this 2 to the power minus L spacings.
Yeah, the spacings being 2 to the minus L is true in any sector. That's a total Z, typical total Z.
All right.
Because those are just power law factors, right? When we restrict to total Z equals 0, it introduces an extra power law factor in the level spacing, but the exponential factor of 2 to the minus L is always there in every sector that's in the bulk of the probability distribution.
There's one more question. Yeah, go ahead.
Yeah. Go ahead.
Yeah. So I was wondering, why did you choose alpha and beta to be that with that convention that like it's flipped on at the ends? Like, wouldn't you want to look for resonances among any states?
Oh, I just wanted to look at end-to-end resonances. Yes, you could look at shorter range resonances. Yes, and people do that. I'm just focusing. See, the point is, I want to look as a function of size, right? So I have a system. It is of a finite size L, and if I say, oh, I'm just going to look at end-to-end resonances, then L is my size. It's the size of my resonance. I don't have to ask, how do I scale the length of the resonance compared to the length of the system, right? So it's just to simplify it a bit, right? You could also study shorter range resonances, yes. But we haven't really focused on that because, then you have to figure out, oh, how do I deal with all that data? And we're talking about sizes, they're just numbers like, 14, and it's like, so, if you say the length of the resonance is the length of the system, then you don't have to worry about, are the fractions, like if I did a resonance of length 11 in a system of length 14, how would I compare that data to other sizes? Because no other sizes have 11/14ths, right? And so it's just to be simpler we focused only on end-to-end resonances. Of course, the shorter range resonances are also of interest, I agree.
I have a question. If one assigns the L-bit string to the eigenstates and then do the procedure, does that?
Well, the idea of this procedure is it is just straightforward with things that, you don't have to, defining the L bits is a highly non-trivial and non-unique thing, right? And so then what you got would depend on the choices you made there, right? And whereas here, we wanted to do it in a way that made no assumptions or assignments of the L bits. It was just about the spins.
Okay, thanks.
And in fact, we're working in the pre-thermal regime where really the L bits don't exist, right? So, although of course you can define them fairly well for finite size systems, but yeah, we want to think about this as you change the size of the system, and it's nicer to just work with the spins so that you don't have those issues coming in. Okay, I forgot to say something. Okay, so we have this, so again, here's alpha, here's beta, right? And say, spin flips up to down, flips down to up, whatever in between. And the process HAB, which connects alpha to beta, flips this spin and it flips this spin, right? And that means, right, the spin flip terms in the Hamiltonian are the J terms, which are just nearest neighbor terms. And so if you just think of how this HAB would be generated perturbatively in a naive way, we expect HAB, this is not very naive, we expect HAB to be of order J over some constant to the F, just because where J is small, the lowest order process, which is end-to-end, will scale like this when you do perturbation theory. If you do it graphically, clearly you're not going to couple one end to the other until you get to an order the length of the system. Okay. Right, and we find that. Okay. But
can I ask a quick question about the
Yeah.
setup? So I think I might have missed some aspect of the setup because I thought alpha and beta would be like neighboring eigenstates in the spectrum, but is it more like they're just chosen to be states with the ends flipped?
there are neighboring states in the spectrum. And of the neighboring states in the spectrum, I'm putting, half of them have this end flipped and half of them have this end flipped. So a quarter of the neighboring states in the spectrum, of which there's exponentially many, are in the category I'm studying.
Okay, so we're restricting.
So it's not, I'm not putting on a big restriction when I say this.
Okay.
So they're adjacent in energy. And of all the ones that are adjacent in energy, I'm looking at the roughly 1/4 of them where they're end-to-end different. That's right. And now, okay, so we find that this is, numerically, we find that this is true. So we also find log HAB has a very broad probability distribution, or I shouldn't say probability, a very broad distribution in each large L sample, very broad and similar. So if we look at the probability distribution of the log of this coupling, versus the log of this coupling. Sort of a Gaussian, vaguely Gaussian looking distribution, and it broadens strongly as we increase L. It's many orders of magnitude wide. But if we ask, say, about the median is behaving like this. Although if we ask about, the extremum here, and I fit it to something like this, the J naught would be very different, right? Because this is exponential in L and this is exponential in L, but with very different sort of factors. And then we're not talking about rare samples, right? So each sample, so each realization of the random fields, when L is large, you get a very broad distribution already, right? So that you don't, to get the broad distribution, you don't need to average over samples. It's there within a single sample, and all the samples have pretty much the same width. Of course, they're different in detail, but they have pretty much the same width. So right now I'm talking about the physics of typical samples. Okay. Okay, and now the crossover MBL, pre-thermal MBL to thermal regime. This is all really within the thermal phase, but crossover in a finite L system from the MBL regime to the thermal regime happens when median HAB is of order when the couplings between the levels are comparable to the level spacing, then all pairs of eigenstates are resonances, and that's really what thermalization is. That's how you get ETH. Every eigenstate is resonant with all the nearby eigenstates, and the eigenstates are made out of linear combinations of many configurations, and you end up with thermalization and ETH. So this is going 2 to the minus 7 number. Now here, let me just make a comment about, you can do MBL in Floquet models which have no conservation laws, so therefore no sectors, and then you really have exactly 2 to the L eigenstates, which are all in the same sector because there are no sectors. Krylov space is the entire space. And then it's a Floquet system, so the eigenvalue of the Floquet operator is on the unit circle, which has a perimeter 2 pi. And so then you know the level spacing exactly, right? So it's not like twiddle 2 to the minus L. You know exactly what the level spacing is. And so in doing this kind of work, it's nicer to work with a Floquet system because of that. You have no issue of what the density of states is. You know exactly what the density of states is. But it's not an important, we do it in Floquet systems and then we compare it to this model, and there's no real differences. So it's it's sort of nicer, but it's not really an important difference. I just thought I'd mention that here. Okay, so now let's go back to our phase diagram here. So here's the crossover. Here's the thermal regime, pre-thermal. And let's go, so if we go right near the crossover, but just on the pre-thermal side, and we look at what's going on, what we find is this. Here's L. Here's log B, which is going as minus L log 2, because it's the logarithm of 2 to the minus L. And then you look at, so this, we look at log median HAB. This is going as minus L log. I'm going to call the factor there Q. So if we're here on this very near the crossover, but on this side, what you find is typically HAB is small compared to the energy difference, so we don't have a lot of resonances. But then as we go to large, this is a linear scale on L, and log things along this axis. As we go to larger L, this slope is smaller than this slope. Q is less than 2. And the crossover is just this line is eventually going to cross this line, and most pairs of eigenstates at large L will become resonant, and the system will presumably thermalize. And that's the simple description of what's going on in this crossover, which I think is a large part of what's actually going on in that crossover. And the interesting thing that hadn't been appreciated that Crowley and Chandran pointed out is that at small L, even when Q is less than 2 and you're going to do this, it starts off with a substantial difference here at small L. So at small L, you're in the pre-thermal MBL regime, even though these are just exponentials. Okay, so that's sort of the simple picture of, to 0th order, what's happening in this crossover. The eigenstates are coupling. The coupling is decaying with L slower than the level spacing, but it's initially at small L quite a bit smaller than the level spacing. So that's why it looks MBL at small L. But then as you go to larger L, eventually the states will couple strongly and thermalize. Okay. So that's that story. And then somewhere here, not very far from the crossover, nowhere near the phase transition, the data gets to something like Q equals 2. And then if we go here, just a little bit past this Q equals 2, what it looks like on the numerical sizes we can access is, here's again the log HAA minus HBB, which is going as minus L log 2. And now the median HAB has got a steeper slope, Q greater than 2, in the regime we can study. And so it looks like the resonances will go away, become rarer and rarer as we go to larger system sizes. But then we have another argument due to the avalanche argument saying this system is actually unstable here. And so that's really where we are here. And I think this is something, this study of the resonances well onto the pre-thermal side of this crossover is just, there have been very few papers focusing on that. And I think what I am expecting is that somehow, if one looks at this very carefully, this isn't a straight line, but it's curved. And there's some process whereby large resonances are produced out of smaller resonances in such a way that this line curves, and eventually Q flows from bigger than 2 to less than 2 as you go to larger system sizes. But that's just a fantasy. And I think this is an area, I'd really like someone to really dig into it carefully and deeply, and see what can be learned here. It's not something I have a project underway on. Right. And now, yeah, and it's this regime here that the papers from Crowley and Chandran and Long et al. Is about. Closer to the crossover. And there you don't have to worry about, oh, does this curve? Because it's going to thermalize even if it doesn't curve. Okay. Now, okay, so that's what I wanted to say about the resonances. So it's sort of, what do we mean? What do we know so far? It's quite an incomplete story. And what I want to do next, how am I doing on time? Okay, so I have a little bit more time, is talk about why do we believe, how did we get this bound on the phase transition? What does that mean? The avalanche bound that we obtained numerically. So that's what I'll do next. But let me just pause again for questions, in case anybody wants to ask anything about this resonance discussion.
I think.
Oh.
There's a question in the chat. Do resonances behave the same way in the case of diagonal disorder? I think it's
Diagonal disorder, what does that mean?
in the case of off-diagonal disorder.
Not sure what a diagonal disorder means.
I guess.
Yeah. If anybody knows what that, if anybody knows what that question means, please explain it. But I think I'll pass since I don't know what it means.
Yeah, I think it means disorder in the J term because.
Okay. That would be off diagonal, but because
yeah,
Hamiltonian, my disorder is on the diagonal in the basis I'm talking about. Well, okay, so if you have the Heisenberg chain and you only have random bonds, there are arguments that you can't have MBL. So that's a special situation because there's a non-abelian symmetry. So certainly things are different there, but if you looked at the resonances, maybe they wouldn't be very different. That's an interesting question. Because yeah, this hasn't been looked at. That I know of. Okay, so now, so we were, right, so we have this phase let me draw my phase diagram here again. So here's the crossover, which is around 0.15. And then, as I said, we have, so this is in the same paper with Alan Morningstar and company, we have this bound on the MBL phase, which is JC less than or 3. So at least a factor of 5 smaller, and it's just a bound, right? So it could be a lot bigger factor. Okay. And so this is coming from the idea of the avalanche, which is meters. $17. Okay, so now this is first, I'm gonna, so we're moving away from, temporarily moving away from numerics to theoretical, and we're going to consider an arbitrarily large system. Okay, so now, so this line is the phase diagram. Now it's a one-dimensional system, and so that, here's my system. This is now space, one dimension. we have, so we're at small j, right? So we're at small j. Okay. Here, we're at small j. And right. Yeah, the fields are random. And in an infinite system, if you look around, you will find a patch, and I'll draw it here in the middle, and it's of length L spins. So this is my rare region where HIs differ only by of order j. So all the HIs are very close to each other here. And so that means it's as if the random field is much smaller, because just by chance here, the local random field in this little patch is much smaller than it is elsewhere. And so here we get a local thermal bath. This region will thermalize and try to thermalize the nearby spins. Okay, so now everything beyond here is typical MBL region. Now, if this L is finite, some number, finite number, this happens with some finite probability. It's exponentially small in L, so it's an extremely low probability. But if I have an infinite system, somewhere in the system, this will be present, right? So these rare regions are present in infinite systems. Right. If the fields are random, drawn from an uncorrelated probability distribution. Okay. And then the question is, can this local thermal bath thermalize the whole system? That's the question. Okay. Is the system stable to that bath? And so now the spins very close to the bath are strongly coupled to the bath, and they will be thermalized by the bath, even though they have fields that aren't similar to in the bath. But if we go to distance r, so let's now go to distance r and ask about, is this bath able to thermalize this spin? Now, it's doing it in both directions. Right? So basically, this initiates an avalanche of thermalization, which spreads in both directions. And the question is, does that propagate forever, or does it stop? Okay. So as a spin, okay, so one way of thinking about this is take the rare region and cut the bonds, just turn the couplings to 0 between the rare region and the rest of the system. And now the rare region is in a thermal state and the rest of the system is in a localized state, right? And if we, of course, there's another rare region maybe way out here, and we'll cut that one away as well. So any rare region that's big enough to start an avalanche, we'll just cut it out, and we'll start with those product states where the avalanches, the rare regions are thermal and everywhere else is localized. Okay. And then we recouple it and ask what happens. Okay. So the spin at distance r, it will be flipped. So in the absence of this coupling here, this spin won't flip. So say this spin is down, right? And this region is MBL, and so this spin won't flip. Right? Of course, it might do some virtual flips, but it'll stay down. almost all the time, right? And then we turn on this coupling here, and now this bath might be able to relax it, right? And so clearly, this is being relaxed by this bond here, right? And so that's a high order process, right? And so we expect it to happen at a rate that's exponentially small in the distance. So at a rate gamma of r going as, and I like to write the exponential this way, that there's a factor which is bigger than 1, a is bigger than 1, and this relaxation rate of this spin, so will be flipped at this rate if the bath is big enough, so that the avalanche doesn't stop, right? Of course, right? If this bath was big enough, this avalanche will go here and it'll relax this spin at this rate. If the bath is too small, the avalanche might stop before it gets to the spin, and then the spin doesn't relax. So that's the scenario, right? And avalanches are going in both directions. Now, actually, I just noticed here in my notes, right? So this is a rare region, right? I did emphasize that, but and this has been known for quite a while, that this is an interesting bit of this physics. And you might ask, oh, how rare is it? And just one sort of empirical sociological statement of its rarity is that if you just look for it in random samples, nobody's ever seen any sign in any numerics, right? So it's extremely rare, right? And it's not playing a role in the samples on the size scale we've been studying numerically. But in an infinite system, it's there, right? And as in terms of a concrete suggestion for an instability of, right, we know MBL is stable at J equals 0. Right? At J equals 0, we know MBL is stable. That's a trivial statement. And as we turn up J and ask, what's the first instability of the MBL phase, which might set this phase transition, this is the first one that has a concrete, comprehensible discussion of what it is and how you might estimate where it happens. So that's why we focus on it. Okay, so, right, now, right, so there's various ways of saying this, but one way of saying it is what I said before. Let's start in this initial state with, these are all localized, the baths are thermal, and it's a product state between the baths and the MBL regions, and then we just turn on these couplings here, and watch the thermalization spread. Watch these spins relax, right? And they will relax at these rates as long as it spreads, right? And let's say that thermalization does get to R-1 here and here, and then we want to ask, or let's say this spin is at R+1. So when it gets to R, we want to ask, is this bath going to be able to thermalize this next spin? So the avalanches have gone to R. So now the bath has L+2R spins. So it's thermalized all the spins out to distance R. And so now the bath is bigger. It's got L+2R spins. And so the bath has level spacing, energy level spacing, 2 to the minus L+2R. I'm calling this delta. Delta is the bath. Delta is the energy level spacing of the bath as it grows. So this is growing as the bath grows. Sorry, this is decreasing as the bath grows. 2 to the minus L, 4 to the minus R, right? Because it's got, as it goes distance R, it picks up 2R spins because it's going in both directions. So it's 4 to the minus R. That's the level spacing of the bath. And then the spin, if it relaxes, will relax at this rate, right? Now, if something is relaxing at a given rate due to a bath, the bath has to look like a continuum to it, right? And so this bath is a bath for spin at R if that requires delta to be less than or of order gamma of R. If the level spacing of the bath is big compared to the relaxation rate of the spin, then the spin doesn't see it as a bath, it just sees it as a discrete set of levels and it won't relax. You can't apply Fermi's golden rule, for example, because there is no bath on that energy scale. So in order for the avalanche to continue forever, you need this to always remain true. And so you need this to decay faster than this. So the conclusion is the avalanche stops if K is greater than 4. So if K is greater than 4, then, right, so initially, this is much smaller than this because of this 2 to the minus L factor, right? The many body level spacing gets a head start because there's a rare region, right? And so the level spacing, and so the avalanche definitely goes a little ways, right? So this starts off smaller, right? But if, it starts off smaller. But if this decays faster than this, eventually this will become smaller than this and the avalanche will stop. So the avalanche will stop if K is bigger than 4. Okay, so the avalanche transition then sub C is K sub C equals 4. And what we mean is, okay, so this is decaying this way in the limit of large R, and that's how I define K. Now, what we're going to see numerically is it's not a simple exponential decay. It has an R dependence, but, and so this would be Kc at infinity is 4. Because when we're saying the avalanche stops, we're saying it can't go off to infinity. Okay, and so we asked, how can we estimate this numerically? So this was all theoretical, but now we're going to look at what this is numerically. And the key step here is this is the decay rate of a spin at distance R if the bath is big enough, right? So we don't worry about the avalanche getting started, right? The avalanche gets started, that's not a problem. The arguments that the avalanche will get started are quite good, and that's not the issue. So we just want to ask a spin at distance R from the bath, how fast does it relax? How does this fall off with distance? If this falls off faster at large distance than 4, K equals 4, then we're in the NBL phase. If it falls off slower than 4, we're not in the NBL phase. The NBL phase is unstable. Okay, so that's the argument, and next I'll go to what we did numerically to try to do that. Any questions before I do that?
David, do you have maybe a few more minutes, I guess?
Okay, so what we did is the following. We made our rare region arbitrarily large, or you could say arbitrarily far away. So we make an infinite bath, and then we weakly couple it to our spin chain. Couple it to spin 1, spin L. So this is weak. And here's my sample, L spins. And then we look at the relaxation rate of the farthest spin from the bath, right? Because the slowest mode here will be the spin farthest from the bath. Okay. So this is now an open system. And gamma of L is the gap of the superoperator, the Lombardian, whatever the superoperator is that generates this open system dynamics. And if you take the limit where this coupling is weak, which is appropriate, so if this represents a rare region which is arbitrarily far away, the coupling of that rare region to spin 1 is extremely small. So we take the limit where this is arbitrarily weak. And then you can write this in terms of the eigenstates of this problem. So you have the eigenstates of this problem. You have a coupling to a bath which is arbitrarily weak. It produces a stochastic dynamics on the eigenstates. So it's just a 2 to the L by 2 to the L matrix in this limit, right? And it was Dries Sells. So Dries Sells has a paper about this, and he was able to make. We didn't take this limit of weak coupling, and we were doing a 4 to the L by 4 to the L matrix because we did the full open system. But he pointed out that you don't. It's fine to take the weak coupling limit here, and that makes the problem numerically much more tractable, which allowed us to go to quite a bit bigger size systems. Okay, so that's just what we do. So we set this up, and we do different lengths, and for each sample, we get the gap. And since we're talking about the gap of the superoperator, the slowest mode, you can use Lanczos, so it's a more efficient thing. You don't have to do a full diagonalization. Although the difficulty here is not that the Hilbert space gets big, but actually that gamma gets so small that it drops below the round-off error. So that ended up being a technical issue, and that's what limited how far you could go with these calculations. Okay, and so now we look at the logarithm of this. We look at a certain percentile of the distribution. Because it was approaching the round-off error, we didn't look at the median, but we looked further up in the distribution. This was, again, Dries Sells' idea, further up in the distribution so that it hit the round-off error a little bit later. So this is a not quite a median, but something close to a median. And now remember, we're asking gamma of L goes as k to the minus L, and we're asking is k, and we can compare k to 4. K equals 4 is the important thing. And now here, when you do this, unlike the resonances, when you do this, there's strong curvature. So there's quite strong curvature on this semi-log plot. So that tells you k is the slope here, and k starts off large and is getting smaller. So k of L drifts to smaller k, and this kind of increases. So given that, but we don't know how to extrapolate because, we don't really have a good theory of anything here. So we just look at the slope at the very end. So we look at K, the slope at the largest L, and then ask, is K of L greater than or less than 4? And again, going to the phase diagram here. So here's J. Okay, so there's a regime where we can see K of L is less than 4 at the sizes we can access, and it's curving this way, so it's going to stay below 4. We go to larger L, there's no reason to think it's going to curve back, right? It should just keep curving the same way. That's the assumption we're making. Given that assumption, which seems pretty safe, any place where we see K of L at our largest L is less than or equal to 4, we're not in the MBL phase. The system is unstable. Now, here, where the Ks we can access are bigger than 4, we don't know it's going to stay below 4 as you go to larger L. And so that's why this JC estimate we have, it's really just a band. The actual transition could be quite a bit smaller. Now you might ask, why is this number so small? And the reason is, at least part of the reason, is that if we look at the, this is getting back to the resonances. So remember in the resonances, I was talking about P of log HAB versus log HAB. This is what couples two adjacent eigenstates. It has a very broad probability distribution, especially if we're down near this phase transition. It's extremely broad. And then if you ask, how does the avalanche spread? So that's a different set of numerics. So I have a paper, Morningstar, HERL, last year. If you ask, how does the avalanche move? So you can do an analysis here and actually start an avalanche with this math and watch it go and ask how it goes. You find it goes through rare near resonances, which are the things way out in the extreme tail of the distribution over here, which have extremely strong couplings in the near resonance. They're not really resonances, but they're near resonances with exponentially anomalously large couplings. And that's what makes this number so extremely small. Is that the avalanche is able to spread through very rare near resonances, which are much more strongly coupled than typical by many orders of magnitude. Okay, my time is pretty much up. Shall I?
There's some questions here.
Write up a bit of a summary, or shall we just go straight to the questions? Or have questions? What do you think?
A summary would be good, yeah.
Okay, I'll try to summarize what seem like the important points. I'm going to erase. Yeah, sorry to run over. Yeah, so one important point, the NBL phase is gapless and critical. So one needs to take extreme care in analyzing it because of that. In most systems, other than one dimension with short enough range interactions, you need to take a non-thermodynamic limit to get the NBL phase. 1B, we have this large thermal MBL regime. In which study near resonances. Of course, it's these resonances and near resonances that make NBL a critical phenomenon. The fact that they're around is what makes it critical. And those are maybe the, since my time is up, those are the points that I think I want to emphasize, just because they're sort of recent and not as widely appreciated as maybe they could be. Okay, so I'll stop there. Thank you.
Any questions? Yeah. There's a mic there.
Can you hear me? Yeah. So in the numerics, you replaced a rare region by infinite path. So is not it a bit oversimplification of the problem?
Perhaps, but yeah, people had tried to do those studies with finite baths, and it was not very satisfactory. I think we have pretty good arguments that this is fine for what we're trying to do, right? All we're trying to do is we're trying to ask, if a spin is at a large distance from a bath, how fast does it relax? How does that fall off with distance, right? And there's no reason to think that that answer to that is sensitive to the bath being infinite versus large, right? Of course, the bath has to be large enough to do the job, right? If you're at, in the NBL phase and the bath is too small, the avalanche will stop. But if the bath is large enough to do the job, there's no reason to think the answer will depend on how large the bath is. It just depends on how strongly you're coupled to it, right?
Okay, there is one more question.
But this is an argument, and one could maybe come up with a flaw in it, but we don't see it.
Okay. And will the growth of the entanglement entropy will be larger than the logarithmic growth in the pre-thermal MBL regime due to the near resonances?
Well, no, the resonances are rare. So it's like it's only once you get to the time scale where the system starts thermalizing that the entanglement will start growing faster. I assume the entanglement, the thing is, the entanglement growing as log time, that's what you're talking about, the entanglement growing as log time?
Yeah. Will it be faster?
I think that, that's all just due to typical stuff. And I think the resonances are not going to add anything significant to that until they become, a large fraction of all eigenstates. And so it's only when the system really starts thermalizing that it will go faster than that, I think. So I don't think that's a place to look for the resonances are there, and you shouldn't look for them in quantities that are averages over lots of things, right? You should just look at the eigenstates themselves and look at the resonances, right? The resonances are resonances between eigenstates, right? The way to study them is to look directly at them. And I think looking at their effects in quantities which are averages over many things is trickier, right? Because they might be very much subdominant to something else.
Okay.
Hi, David. This is David Long.
Hi.
I think I asked you this question before. but I figured I'd ask again just to see if the answer has changed in like the year or so since the last. You talked about like this drift in like what you called Q, right? In the resonance counting. So in our PRL, we did like propose a mechanism, even if we didn't do anything quantitative with it at the time, with this like successive resonances, which could change Q. I guess we called it theta, but it's fine. But do you anticipate that there has to be another mechanism, or is it just like a quantitative study that is lacking?
Well, I guess I would like to see a quantitative showing of the effect, and then that dissected to see the mechanism. If you really understood it, you would be able to, well, if it was visible quantitatively in the numerics, you should be able to dissect it and demonstrate what the mechanism is, right, in the numerics. That's what I would really like to see, but maybe that's just asking too much. Does that address your question?
Yes, thanks.
So David, I mean, if one looked at some like a transport coefficient, like let's say the spin conductivity or something, I mean, does that show as a function of J? Does that show signatures of the crossover? And I guess at the transition, it should go to 0, right? It should vanish. But does it show any signatures of the crossover from the to the pre-thermal?
Well, the localization, if you have a model, so first of all, MBL happens in models with no transport, right? And so transport is not part of MBL. MBL can affect transport in systems that have transport. And so I think looking at the transport is a very indirect way of looking at the MBL. So I think, I don't find that as promising. But yeah, certainly the MBL will slow down the transport, but I don't know that.
But I thought you said you
sort of feel like that's
for the system to at all. I mean, before we can talk about thermalization, you need transport, right? I mean,
no, you don't. If you have no conserved quantities, you have no transport.
No, but here's, let's say you have magnetization is conserved, right?
Yeah, in this model, right? But we look at models that are Floquet models with no conserved quantities, and they behave the same. So the phenomenon of MBL is not about transport, right? It's about thermalization.
But if you don't have transport, I mean,
systems that have no transport. So transport is not part of MBL. MBL affects transport if your system has transport. But MBL occurs in systems that have no transport.
Right, but for this system which has transport, I mean, MBL phase, it should be 0, right? So, I mean, the conductivity should be 0. But I'm saying, like, is there I mean, in the crossover between the pre-thermal and the thermal phase?
Well, we don't even understand the transport in the thermal regime, right? So in that model, the transport is weird in the thermal regime for reasons that we don't really understand, right? So the transport doesn't look like a promising thing to make progress on understanding MBL, right? Of course, understanding the transport in this model would be nice, but we can't even understand the transport well away from the crossover in the thermal regime. It's doing weird things, as people have reported. And it's really just not understood yet. And I feel that's like a separate problem, which is about the transport in that regime. And that's not, it's just a symptom of MBL, but it doesn't look like a promising direction to learn more about MBL, you will just learn about how MBL type physics affects transport in that kind of model. But that's my attitude about that. It's not that it's an interesting problem, but it's a different problem, I think.
About this argument of the avalanche, suppose I want to make this argument with something that looks like a two-leg kind of chain. It seemed that this factor that was like imagine a two-leg ladder of spins.
Yeah. With a qubit at one end of each rung of the ladder.
Yeah, this.
So now it's got four states per site. Yeah, that's just a one-leg ladder with that's just a chain with 4 states per site, right? And the factor of k that I call, so the k equals 4. That's 2 squared, where 2 was the dimension of the Hilbert space on site.
Exactly.
So so that would just change this k into 16. So the kc, instead of being 4, it would be 16. So more generally, kc is d squared, where d is the dimension of the Hilbert space on a single site.
Yeah.
And we're measuring length in terms of sites.
Right. So it seems that if you increase the number of legs in the ladder, then the MBL transition would become even a smaller J.
Oh, absolutely. Yeah, no, in 2 dimensions, the MBL transition is not there in the thermodynamic limit.
Yeah, so if I take a 2-leg ladder, maybe
So that's what
completely
you'd expect.
rule out?
As you make it more 2-dimensional, the MBL phase will shrink. That's what you expect. And that's what undoubtedly happens. Well, people have certainly seen this.
So, but can it be completely ruled out even, for example, for a 2-leg ladder with this same type of simulations that you did?
What do you mean ruled out?
To show that this K never goes below the critical value, or would you just push the as a function of J?
No, K is just going as 1 over J. So you can make K arbitrarily large.
Okay. Okay, so there will just be a smaller J.
I think so. Yeah.
Okay.
Yeah.
Okay.
If there are no more questions, let's thank David again. Thank you, David. I think it's all done.
Okay, I'll see you. Good
Bye-bye.
night.